Hey everyone, in this video I'm going to talk about causal inference with observed confounders. So when we introduced the idea of causal inference and estimation techniques for causal inference last week, we talked about it in the context of experimental designs. So those are designs where we have basically a random assignment mechanism with some probability of assigning each observation, each unit, to either a treatment group or a control group, right? In practice, and depending on your substantive field of interest, oftentimes either for logistical or ethical or financial, due to financial constraints, it's often difficult to actually, implement such a randomization or randomized control trial. Either difficult or it might even be impossible, depending on your substantive field of interest. Okay. So now we're going to talk about causal inference when we don't have basically the luxury of implementing an experimental design, but have to rely on observational data. Okay. And there are a couple of additional challenges that come with analyzing observational data if our goal is causal inference. Okay, and remember from last week when we talked about the assumptions for causal inference and the virtue of basically perfect or randomized experiments is that with randomization, the treatment assignment itself is ignorable in the sense that it's independent, or the distribution of potential outcomes is the same across the treatment variable or across the treatment group and the control group, right? And what this allows us to do is to say, okay, treatment group and control group are basically comparable, they're balanced, they're equal in all kind of potential confounding factors. So when we examine the difference between the treatment and control group in our experiment, in our experimental design, we can attribute any difference that we observe to the treatment, to the intervention itself. Okay, and now in observational studies, things are a little bit more difficult. Because in observational studies, we have non-random assignment to treatment and control groups, right? By definition, in an observational study, we don't control who gets the treatment and who gets the control and who is in the control group. Okay, and that makes things a lot harder because that can lead to selection bias, certain observations selecting into the treatment group, on certain observations selecting into the control group due to confounding variables. Okay, so if we have basically other characteristics that are related to whether observations end up in the control group or end up in the treatment group, and those confounding variables also affect the potential outcomes or related to the potential outcomes that we're ultimately interested in, okay, then ultimately we will induce bias. We can't just simply compare differences between the treatment group and the control group because there are systematic differences between those two groups above and beyond just the difference due to treatment assignment, okay? Or in other words, if we have non-random assignment to treatment and control groups, the potential outcomes are not equally distributed across treatment and control anymore, and so ignorability doesn't hold anymore. Okay. Now the good thing is there is one potential way around this, and that is basically if we observe all of these confounding variables, all of these variables that affect both whether or not an observation ends up in the treatment group or control group, and also that impacts the outcome or the potential outcomes essentially. Okay, so in a case where we observe all potential confounding variables, we can use regression, basically the techniques that we talked about throughout the semester, to adjust for these confounders. Okay, but the key is that requires very strong assumptions. Okay. One of the most crucial assumptions that is essentially untestable is that we have no omitted variables, that we observe all potential confounding factors, okay? All variables that potentially impact treatment assignment and also potentially impact the outcome itself. And we have to be able to basically adjust for all of them, okay? But the key is also that the assumptions don't end there, right? If we use regression, all of our regular regression assumptions about linearity and so on also have to hold, okay? But if that is the case, if we can assume that we observe all confounders, that we observe all these factors that impact treatment assignment and the potential outcomes themselves, then we can basically assume conditional ignorability. So in other words, despite, in comparison to the true experiment, where the potential outcomes were just independent of the treatment assignment itself, now we're basically saying, after conditioning on all these potential confounders that we might have, after conditioning on those confounders, the treatment assignment or the potential outcomes are independent of the treatment assignment. Okay. So in other words, in this context, kind of conditional ignorability basically reflects the assumption that the researcher can ignore the model for the treatment assignment as long as the analysis regarding the causal effects ultimately condition on the predictors needed to satisfy it. Okay. So in other words, if ignorability holds, if we're basically adjusting for all potential confounding factors, we do not need, we essentially don't need to model the treatment assignment mechanism, and we can basically proceed to compare treatment and control groups in a regression framework, for example. Okay. But again, the key is that this assumption of no omitted variables and no selection bias, conditional on the confounders, is a strong and untestable assumption. And the underlying assumption is, again, that we observe all potential confounders and that we properly control for them. We also assume that we use the right, functional form, the correct model specification, and so on. Okay. There's also additional concerns in the regression framework when we, even if we, control for all potential confounders, we have no omitted variables, and we, potentially have our remaining regression assumptions met. There's still additional concerns when we talk about when our goal is not only prediction but actually causal inference. Okay, and these concerns are focused on the questions of balance or lack of balance and overlap. Okay. Overlap, also called common support in the literature. So what does balance and overlap mean? Okay, balance basically refers to the distribution of, or the comparison of the distribution of potential confounding factors across the treatment and control group, right? And so this could basically imply, for example, that the average level of some confounding factor, it might be, for example, in a survey experiment, maybe older people react differently to your treatment, and so or are more affected by the treatment, and so. Or select into the treatment, basically, or more likely to select into a certain treatment. Suppose, for example, we're interested in examining the effect of certain, media exposure on political attitudes. Okay, but of course, older people, tend to view different types of media sources than younger people. Okay, so here. Age kind of is related to the assignment in the sense that the treatment is exposure to a certain media source, for example, but it's also related to the outcome, for example, political attitudes or something like that, right? So in that sense, if we just look at this from an observational in the context of an observational study, we have an issue with imbalance, because essentially this confounding variable, like the age distribution, is different between the treatment group and the control group. Okay, this could be here on the left. Okay, so that the average age in the treatment group and the average age in the control group differ from each other. And to the extent that that age is related to the potential outcomes that we're interested in, that will ultimately bias our estimates. Okay, but imbalance can be more subtle than just differences in averages. Okay, we can also have imbalance between treatment and control group, and this is here on the right side, where even though the averages are the same, we can still have differently shaped distributions with a different skew, and that can still impact our estimates, our comparisons between the treatment and control group, depending on the underlying data generating process. Okay, so that's imbalance. Okay, imbalance with regard to confounding factors between the treatment group and the control group. Okay. The next issue that is related, but it's not exactly equivalent, is the question of overlap. Okay, and by overlap, we basically what we mean by that is to what extent the distribution of these confounding or these distributions of confounding factors overlap. Okay. So if we have no overlap whatsoever, that would basically mean like that all in the example that I mentioned earlier, all old people select into one media source, all young people select into another media source. There's no overlap where people in the same age group where people in the same age group kind of use the same kind of type of media source or something like that, for example. And so in a case like that where we have no overlap whatsoever, it's basically impossible to estimate the effect of the treatment itself, because we don't have appropriate counterfactuals within each kind of group with respect to the confounding variable. Okay. On the other hand, we can have partial overlap, which means that the distributions, there is some overlap in those distributions, okay, but it's not perfect, it's not complete, okay. And the important thing to recognize here is that if we have issues such as partial overlap in this distribution or in this distribution, that means that ultimately this restricts the amount or the types of causal inferences that we can make. Okay, because ultimately, in order to make valid causal inferences, we need basically control groups or comparison groups that are comparable, right? So essentially, in this center graphic right here, where we have partial overlap, basically the causal inferences or the treatment effects that we can estimate can only ever tell us something about the treatment effect among basically observations that fall within that range of the underlying confounding factor, right? Because only for this range, but going back to the age example, for mid-age ranges, we have actual observations that either fall into the control group or fall into the treatment group, right? And so only for that age range can we make basically inferences about the effect of being in the treatment group or being in the control group. As soon as you're outside of that range, either here to the right or here to the left, you don't have valid counterfactuals anymore, right? You don't have observations that are similar in terms of that confounding factor, but that actually selected into the treatment group, or that are similar and selected into the control group, right? So lack of complete overlap ultimately limits basically the types of observations for which we can make valid causal inferences. Okay. Another related problem or a resulting problem is that if we want to make kind of inferences about ranges ranges of observations that kind of fall outside of this overlap, ultimately our inferences will be much more model dependent. Okay, and in order to kind of illustrate why that is the case, we can look at a couple of different plots based on one of the examples that is discussed in the textbook, where we examine the basically the relationship between post-test scores. I think this is the child reading scores, and as a predictor, the pre-test scores. Okay, and this is an example where if we look on the upper left here, where we don't have complete overlap, in the sense that observations on the lower left here with very low pre-test scores only ever ended in the in the control group, so they never received this treatment. Okay, so there's no, basically the gray dots here are control groups, control group observations. The darker dots are treatment group observations. Okay, so if we look at that range for the lower range of pre-test scores, we see very few or no observations that actually were assigned to the treatment group, right? So this is kind of comparable to this graphic right here, where we have only partial overlap. Similar in the higher end of the distribution of pretest scores. Up here, we only have observations in the treatment group and no observations in the control group. Again, no overlap. We don't have these counterfactual observations available, right? And further, suppose that these solid lines here represent the actual relationship, the true relationship between the pretest score and our outcome of interest, the post-test score. So there's a nonlinear relationship, the solid line here for the treatment group, and this solid line here for the control group, right? So now suppose we want to estimate treatment effects conditional on pretest scores, based on a linear regression model. And the key here is that on the left-hand side, we have a basic regression with the pretest score as a predictor, as well as the treatment assignment as a predictor, without an interaction. So these two dashed lines are parallel to each other. Okay, so no difference in slope. Okay, and based on kind of that treatment or that linear regression model, we can estimate a certain treatment effect, which of course is equivalent to the difference or the kind of the intercept shift between the two dashed lines. Okay, and since we don't include an interaction, we basically assume constant treatment effects. So this difference or this intercept shift is constant over time, right? Now suppose that instead of or in addition to this model specification, now we include an interaction term, because now we suspect that there might be a heterogeneous treatment effect for different levels of pretest scores. Okay, and so here we see two dashed lines for regressions that were basically for two regression lines where we included an interaction term, so there's a slope difference in addition to the intercept shift, essentially, right? And so now we have basically conditional on pretest scores, we have smaller treatment effects on the lower end and larger estimated treatment effects on the upper end. Okay, the point is, or the key insight here is that because we have a lack of overlap, for these areas, particularly for the areas where there is no overlap, our estimated treatment effect is very dependent on our model specification. So whether we include an interaction term or not include an interaction term, our estimated treatment effect is very different, right? Here it's much larger than here, or on the lower end it's much smaller than here, including an interaction, than it is here, right? So that ultimately means that if we don't have a complete overlap, then our inferences basically outside of the overlap range are highly dependent on our model specification. Whether or not we have the correct model specification, of course, we cannot directly, test from the data, right? So we're basically left with hoping that we have the correct model specification. Okay. Now, what we can do to kind of solve this issue is we can restrict our observations to the region with overlap. So basically, rather than looking at the full range of the data up here, we now look at basically just the slice of pretest scores for which we have complete overlap, where we have observations that fall into the treatment group and fall into the control group. Okay, and basically now if we basically just restrict our sample to basically the range between pretest scores around this area and this area, we now have kind of the same scatter plot with treated and untreated groups, okay, where we can now again estimate treatment effects based on a linear regression model, okay. But the point is that now, similar to the upper two figures here, in the lower two figures, we included on the left-hand side no interaction term, and on the right-hand side, we included an interaction term, okay? And so now that we restricted our observations to the region with overlap, whether or not we include an interaction term or not actually leads to very comparable, very similar results, okay? So that's what we mean by saying if we basically have overlap, then our inferences are less model dependent, right? It doesn't matter so much anymore whether or not we include an interaction term. The difference in the kind of estimated treatment effect for lower and upper ranges of pretest scores are much smaller, right? So there's less of an issue with misspecification, okay? Okay. And this idea of basically restricting our observations to the region with overlap directly brings us to the topic of matching. Okay. One thing I should say before we move on to matching is, of course, that also means that the treatment effects that we're estimating are a little bit restricted in the sense that we can now only make basically statements about the treatment effects within the range that we restricted our analysis to. So basically within the range where we had overlap. So we are more certain about the treatment effects that we're estimating in that range, but we know that since we have overlap, that these estimates should be less model dependent, okay? Now, as I mentioned, this, let me see, brings us now to the topic of propensity score matching, okay? So again, assuming that we're willing to trust this ignorability assumption that we're basically measuring all potential confounders, we saw that we can adjust using regression, but there are issues with functional form assumptions, to what extent our regression assumptions hold, and so on, right? So the question is, can we make these adjustments by adjusting for potential confounding factors with fewer parametric assumptions than regression? And propensity score matching kind of helps us basically restrict observations to only sets of observations that basically are comparable and therefore allow us to make these comparisons between treatment and control group, for example, then using regression again, okay? So the basic idea of matching, and in particular propensity score matching, is to restructure the original sample such that treatment and control group exhibit balance and overlap with respect to the pre-treatment variables that we consider to be confounders. Okay, so again, we have to measure all the confounders. We're still assuming no omitted variables, but we're now basically restructuring the sample such that treatment and control groups are balanced and exhibit complete overlap. There are different ways of doing that. There are different potential strategies. One potential approach could be to remove some observations. This is kind of the example that I kind of illustrated here, where we remove observations that simply don't have overlap, for example. Or we could also use weights to either increase or decrease the influence or impact or the contribution of certain observations, okay? And there are lots of different kind of techniques To do this, we won't kind of go into those into too much detail. We'll talk a little bit more about them in the Q&A session, but just the overall idea is to restructure the sample such that treatment and control groups are balanced and ultimately have overlap. Okay. One very common technique to achieve this balance and overlap is to match based on propensity scores. Propensity scores are basically describe the probability that any unit in our data receives the treatment given the pre-treatment covariates that we observe. Okay. They're different. There are other techniques to reweighting and matching, but the most common kind of summary to evaluate whether certain observations are comparable to each other is by evaluating and comparing their propensity scores, so their relative probability to belong to the treatment group or belonging to the control group. Okay. And again, I will go through this very quickly here, and in our Q&A session, we'll go through this in a little bit more detail with an actual applied example. But essentially, if you want to use matching kind of as a data pre-processing step to get around this issue of a lack of balance and overlap, before you run your regression, just the way we kind of talked about it here, there are essentially 5 different steps you go through. The first step is to define the confounders and the estimate. Okay, so we have to define all the potential confounding factors that we have to control for, and also we have to define our estimate. What we mean by the estimate is basically what our what the focus of our inference should be, right? Are we interested in estimating the effect on everyone who received the treatment? Then we basically leave that that group of observations intact, and we try to restructure the control group to resemble that treatment group. Or are we interested in estimating the effect on observations in the control group, and then we leave that group intact and kind of match or try to kind of restructure the treatment group in order to resemble that distribution of the control group. Okay. So after we did that, we can then proceed to estimate the propensity score, and that usually, implies we're estimating, for example, a logistic or probit regression where the outcome is essentially the assignment to the treatment versus control group. Conditional on all our confounding factors that we previously identified. Okay, and this allows us to then have a predictive model of belonging to the treatment group versus the control group. Okay, then we use this estimated propensity score, this estimated probability to belong into either group, to match comparable observations. So basically, the closer these propensity scores are to each other, the more comparable these observations should be across a wide range of covariates or confounding factors. Okay, again, there are a lot of different matching algorithms of how we want to match observations based on the propensity scores, and we'll talk a little bit more in detail about those in our Q&A session on Monday. Then the next step, after we matched our observations, we want to check diagnostics for balance and overlap. Okay, and one kind of common way of examining this is to look at these balance plots where we examine the absolute difference, for example here, the absolute standardized difference in means across a certain set of confounding factors between the treatment and control group. Okay, and so here these white or hollow dots are basically the differences between treatment and control prior to matching, and we see, for example, in this study there are quite strong imbalances in birth weights and days in hospital. This is about children. There was a program for infants to support kind of early birth infants, I believe, and then after after matching, these are now the darker dots here, we see that there's now almost no difference in these pre-treatment confounders with regard to many of those covariates. We can also see that oftentimes there's a kind of a trade-off between balance in one confounder versus another confounder. So after the matching, we have basically a pretty good balance with regard to the first three confounders, but kind of the trade-off was that confounding or the imbalance with age was slightly increased. That's quite usual to see such trade-offs between balancing, some covariates versus another. Okay. Then after we kind of reweighted our data or removed some observations and achieved now balance and overlap across our observations, we can now estimate our treatment effects based on the restructured data. And the key is here we can, on the one hand, we could just look at a difference in means between the treatment and control group, but we can also still run our regression, including pre-treatment covariates, and controlling for those and potentially looking at heterogeneous treatment effects and so on, just based on the matched or restructured data. Okay, so this kind of concludes our discussion of causal inference with observational data. Again, all of this is based on the crucial and untestable assumption that we observe all potential confounding factors. Okay, so all variables that impact whether or not you land into the treatment, land in the treatment or control group, and that impact the potential outcomes or the outcome of interest, that all of those are measured and are accounted for. And that's a very strong assumption that we are not able to test from the data, and in many cases it's simply not very realistic. Okay. When it comes to kind of choosing control variables, I also want to emphasize that on Canvas, I included an additional paper that I mentioned in the past on that provides some guidelines as to how to choose confounders and what confounders to control for and what variables not to control for beyond the general advice not to control for post-treatment variables. So make sure to check out that reading again if you haven't done so already. Okay. But as I mentioned, that's the kind of the overview of causal inference with observed confounders, where we basically have all our potential confounding factors measured and accounted for. And now in the next video, I'm going to talk about causal inference with unobserved confounders, where we didn't measure all of these factors that impact both treatment assignment and the potential outcomes themselves.